start. I'm going to start recording. So we didn't finish section 4, chapter 10 last time. Can you still hear me? Is it good? Everything's working? Can everybody hear me? Hello? Okay, great. Just make sure we're in the same page. So we talked about polar coordinates and the polar graphs last time. Polar coordinate system is a different coordinate system from the rectangular coordinates. You use r and theta instead of x, y to describe the points and the curve on the plane. And the two coordinates r theta essentially means the directed distance, okay, from the point to the pole, and theta is the polar angle measured from the polar axis. Okay, so we have some positive and negative values for r and theta in general. But we usually use positive values for r to avoid the confusion. On the other hand, we use negative values r quite a bit. Okay, sometimes it's even more convenient. So if you rotate counterclockwise from the polar axis, you get the positive angle. If you rotate clockwise from the polar axis, you get the negative polar angle. And we don't talk about the x-y axis in this coordinate system. Of course, we have the pole, which is the origin of the rectangular coordinate system, and we have the polar axis, which is the half positive x-axis. All right. Okay. Polar coordinates are very convenient in describing circular shapes, but it's not convenient to describe straight lines. Okay. So when we try to find the slope of tangent lines, okay, using polar coordinates, we have to convert it back into rectangular system using the conversion formulas we discussed last time. Okay, x equal to r cosine theta, y equal to r sine theta. So r equal to f of theta is the plane polar curve. Okay, so we don't have x and y, but we have r and theta, r as a function of theta. Okay, so instead of y equal to fx, we have r equal to f theta, which gives you a polar. So you can think y equal to fx in the rectangular coordinates. You get a curve. So in the polar coordinate system, r equal to f of theta also gives a curve. All right. And then you can find the slope of tangent line at any point on the curve shown on the graph. The red curve, we have a point r theta on the curve, and there is some straight line. There's tangent line to the curve at that point. So the slope of tangent line is just dy over dx in the rectangular coordinate system. If you converted it back into the rectangular coordinates. But we can write x, y both as functions of theta, okay? Given r equal to f of theta, right? So x equal to f of theta times cosine theta, and y equal to f of theta times sine theta. So then you can use the formula for tangent line or slope of tangent line for parametric equations. You take the derivative of y with respect to theta, the parameter, over the derivative of x with respect to theta. Both are functions of theta. All right. And then, for horizontal tangent, the vertical tangent, that we got dy over d theta equal to 0, and dx over d theta equal to 0. All right. So these are some general discussions of the tangent lines in polar coordinates. So let's just do one example to find tangent lines or slope of tangent lines for plane curves in polar coordinates. So in this example, we define the horizontal and the vertical tangent lines to the curve r equal to a times sine theta. Okay. So r equal to a times sine theta, that's a polar curve, a curve represented by polar coordinates. So here r and theta are variables and a is a constant. Okay. So the strategy here is to rewrite the x and y both in as function of theta. Okay, so we just convert it back to the rectangular coordinates. We can definitely do that. So x equal to r cosine according to the conversion formula. But r is just a sine theta for the curve. So we got x equal to a times sine theta times cosine theta. And if you use the double angle identity in trig, you get a over 2 times sine 2 theta for x on the curve. Okay. For y coordinate, any point on the curve, the y coordinate y equal to r times sine theta by using the conversion formula. But r equal to a times sine theta for the curve, so that y equal to a times sine theta times sine theta, or a times sine theta square. And you can also use the double angle identity in trig to rewrite that as a over 2 times 1 minus cosine 2 theta. So then we have x and y both as function of theta, the polar angle. So just use the formula dy over dx equal to dy over d theta over dx over d theta. Okay, theta is the parameter. Just treat these two functions as parametric equations, and then plug in y and x. Y equal to a over 2 times 1 minus cosine 2 theta, and x equal to a over 2 times sine 2 theta. And then you just take the derivative of those two functions, so we get a over 2 taken out both on the top and at the bottom. And then you just take the derivative of trig functions with respect to theta on the top and the bottom. Okay, so then we can cancel a over 2 on the top and the bottom. So then you take the derivative of 1 minus cosine 2 theta, you're going to get the 0 minus negative sine 2 theta times 2, because 2 theta is a function of theta. So you need to use the chain rule. What you do is multiply the derivative of 2 theta. You get 2. That's how you get 2 on the top. And similarly, you get cosine 2 theta times 2. And the 2 outside is also coming from the chain rule. So that's the derivative of sine 2 theta. And then, you do a little simplification on the top. You get the 2 negative signs, so it becomes positive, and you don't have to worry about the 0. So it's 2 times sine 2 theta over 2 times cosine 2 theta, which is tangent 2 theta if we want to write, simplify it. So when we talk about horizontal tangent, then the slope is 0. So dy over dx equal to 0. So that means sine 2 theta has to be 0, and because dy over dx is just the 2 sine 2 theta over 2 sine cosine 2 theta. So 2 theta or sine 2 theta equal to 0, we solve that trig equation. It gives us two solutions. Either 2 theta equal to 0, 2 theta equal to pi. Those are all the values of 2 theta from the angle between 0 and 2 pi. All right. So then you're going to get theta equal to 0, theta equal to pi over 2 if you divide by 2. So there are 2 points on the curve where the horizontal, the tangents are horizontal. And for the vertical tangents, we want the cosine 2 theta equal to 0. Divide with dx again is equal to 2 sine 2 theta over 2 sine cosine 2 theta. So when the denominator 2 cosine 2 theta is 0, then the slope is undefined and we get vertical tangent. Or you can say dy over dx is equal to infinity. Okay. So we just solve the equation of cosine 2 theta equal to 0, and we got two values for 2 theta from 0 to 360 degrees. Is either 2 theta equal to pi over 2 or 2 theta equal to 3 pi over 2, 90 degrees or 270 degrees. All right. Again, just divide by both sides for those two equations. You get theta equal pi over 4 or theta equal to 3 pi over 4. All right. So then we can graph this curve. If you graph the curve r equal to a times sine theta, you're going to find that is a circle on the upper half plane tangent to the polar axis, and the radius is just the a, and the center is just about the pole with different distance. A is like this shown in the graph. So you can see there are two horizontal tangents on the top one and the bottom, and that corresponds to theta equal to 0. Okay, the bottom tangent, and theta equal to pi over 2, the top tangent. You get if you draw the line from the pole to the top point, you get the perpendicular line to the polar axis. So theta equal to pi over 2, right? And the other two vertical tangents occurs at left and the right with theta equal to pi over 4, 45 degrees on the right. Oh, 3 pi over 2, 135 degrees on the left. You can see on the circle. Okay. So that confirms our result. So that's the example, in tangents in polar coordinates. So, you have to know a little bit about the trig identities. All right. Any questions? So we just completed chapter 10. We're going to go to the next chapter, chapter 11, if you don't have any questions. We're going to do 11.1 now. So we have a few pages. Okay, so chapter 11 is vectors and the geometry of space. All right, so we're going to talk about vectors as a powerful tool in starting geometry in space. And we're going to use some calculus here a little bit, and we're going to talk about how to use vectors to describe different objects in space. Let's talk about the vectors in the plane first. in section 1. So we are talking about the two-dimensional space. So the plane x, y plane. So we come back to the rectangular coordinates, all right? So let's say we have one point P and then another point Q on the plane with coordinates P1, P2, and Q1, Q2. And then we can draw a vector from P to Q. So what is a vector? It's the direct line segment from point P to point Q. So you have a direction for the vector. In other words, it's directed. So it points from P to Q in this case. And the notation for vector P is just you put the arrow on the head of PQ. A vector has both direction and length. All right. So this is the important feature of vectors. But keep in mind, any physical quantity with the direction and the length are not necessary vectors. Okay. For example, current is not vector. The flow of water is not the vector. Okay, so be careful about this. All right, and then the vector PQ have a length, just the length of PQ. If you use the distance formula, that's just square root of Q1 minus P1 square plus Q2 minus P2 square. But we call P the initial point and Q the terminal point. Okay, for the vector. And vector PQ can be represented by component form using a bracket. What they do is just subtract the coordinates of the initial point from the coordinates of the terminal point. So Q1 minus P1 and the Q2 minus P2. And they are the components of the vector PQ. All right. So this is called the component form of vector. Especially if P is at the origin, okay, then the vector PQ written in the component form will be Q1 minus 0 and the Q2 minus 0 because P1 equals 0 and P2 equals 0. So that's just the bracket, the Q1, Q2. All right. So be careful about this notation. If you use parentheses, that means a point, like a P1, P2, parentheses P1, P2. That's a point. But if you use a bracket, Q1, Q2, then that's a vector. All right. So that's the difference for the notation between a point and the vector. Especially the zero vector, we put a 0 and the arrow on the top of it. It has both components 0, all right? In other words, the length of the zero vector is 0, as we already know that before. Excuse me. One important property about vectors is they can be moved freely if you keep the direction and length unchanged. Like the three vectors, V1, V2, V3, they are the same. Okay, for example, if you talk about the velocity of a car, you really don't have to specify where the car is because you're talking about the velocity, not the position of the car. All right, so it can move freely without changing the direction of the lane and the length. Okay, so let's do one example. A vector u is from point -40 to point 18, and then that vector v is from point 2 -177. Find the u and the v, vector u and v, and the length of u and v. By the way, if you put a double vertical bars, uh, on the vector, sandwich the vector, then that means that we're talking about the length or uh, the what the length of a vector. All right. So let's just find the vector q, u, and v first. So to find the vector u, you just subtract the coordinates of the 2 points. So the initial point is -4, 0, and the terminal point of 1 is 1, 8 for vector u. So you just subtract the 1 and -4, 8, and the 0. Terminal minus initial point. Okay, so we get 1 plus 4 and 8. So that's 5, 8. For vector v, we can do it similarly, and the initial point is 2, -1. The terminal point is 7, 7. Okay, from the 2, -1 to 0.77. So that's 7 minus 2 and 7 minus -1. So we get the 5, and 7 minus -1 is just 7 plus 1, which is 8. So we got the same components of v as u. So that means two vectors are the same. Okay, if you have the same components of two vectors, then the two vectors are identical. And then we can easily use the formula for the length of the vectors. So the length of vector u is equal to length of vector v. That's equal to 5 squared plus 8 squared. So what you do is just take the square root of the sum of the squares of the components. So 5 squared 25, 8 squared 64. You get the 89 if you add them. So that's square root of 89, the length of the two vectors. And these two vectors are drawn in the graph. As you can see, they are in the same length and point to the same direction. So these two vectors are actually the same. All right? So that's easy. So let's talk about the operations on vectors. So suppose we have two vectors, u and v, with components u1, u2, and v1, v2 separately. Then you can add, subtract the vectors, and you can multiply a scalar, a number, to a vector, and you can also add and subtract using either components or algebraic way or using geometry. Okay, so it is very convenient to use components of vectors when you do these vector operations. For example, if you add u and v, you just add the components of the two vectors. So you're going to get the u1 plus v1 and u2 plus v2. Similarly, if you subtract two vectors, you can just the components of two vectors. So you get the u1 minus v1 and u2 minus v2. If you multiply a number, a scalar, to a vector, then you just distribute the scalar or number into the components of this vector. So cu equals just cu1 times and cu2. In a special case, if you put a negative u, you just negate both components of u, so you get a negative u1, then negative u2 for the components. So this is how you do vector operations by algebra, but you can also do those operations by geometry. For example, if you have two vectors and you want to add them, you just move one vector and then draw a triangle. So, for example, if you want to add the vector u and v, you're going to move the initial point of v to the terminal point of u. And then you just draw a vector from the initial vector of u to the terminal point of v to get u plus v as shown in the first triangle. Okay, and when you do the subtraction of a difference of two vectors, then you're going to put the initial points of u and v at the same point. Okay, then u minus v will be the vector from the terminal point of u to the terminal point of v, terminal point of v to the terminal point of u. Okay, so that's how you do add and subtraction, vectors in geometry. All right, so let's just do some simple examples by using algebra. So let u vector u equals -3, -8, and v vector v equals 8, 25. We need to find 2/3 u, v minus u, and the 2u plus 5v. Okay, so for 2/3 u, you just distribute 2/3 to the components of u, so you just multiply 2/3 with -3 and -8. So you're going to get the -2 and the -16/3 if you know how to do multiplication with you should. So this gives 2/3u, which is another vector. Okay. V minus u, which is 8, 25 minus -3, -8. So what you do, just subtract the x and y components separately. So 8 minus -3 and 25 minus -8. So 8 plus 3 is 11 and 25 plus is 33. For 2u plus 5, you just multiply u by 2 for the components, and the 5 to the components v and add them up. So you get 2 times -3, -8 plus 5 times 8, 25. So then you distribute 2 in the first term, you get -6, -16. And you distribute 5 to the second term, you get 5 times 8, which is 40, and 5 times 25 is 125. And then you just add x components and y components separately for those two vectors. So you get the -6 plus 40, which is 34, and the -16 plus 125, which is 109. So these are the components for the new vector 2u plus 5v. Okay, it gives you another vector. All right. All right. So there's some other properties of vectors. So u plus v is equal to v plus u. Okay, so this is the commutative law. It also holds for vector addition. U plus v plus w is u plus v plus w. So you can add them in any combination. So that's the what the law is, the I forget. Okay, so that's another law for real numbers additions, right? Okay, and u plus 0 is just the u. Okay, just like the numbers, vectors, you do the same thing. U plus -u is 0. It's also like numbers. C times du is just c times t times u. Okay, so for the scalars c and d, for numbers c and d, you can multiply them in different orders with the vector. For c plus d times u, you can distribute the u to c and d, you get the cu plus du. And for c times u plus v, you can also distribute the c to get the cu plus cv. So distribution holds for for vectors. 1 times u is just the u. 0 times u is just 0. So everything is just like numbers. All right. The only difference is you get the answer as vectors instead of numbers. Also, okay, I think there's a typo here. What dash up, you know, I wanted to write is the length of CU is equal to the absolute value of C times the length of U. Okay, so I'm going to correct it. You get the absolute value of C because the length of CU is always positive. Okay, but the C itself can be negative. So in order to make the whole thing positive, you need to take the absolute value of C. All right. So this is typing here. Okay, now let's type the unit vector in the direction of V. So you get the arbitrary vector V. How do you find the unit vector in the direction of V? Easy. You just divide by V by its length itself. So that will give you a unit vector. Okay, unit vector is the length of the new vector is 1. But at same time, you still have the same direction with V, right? Because you divide by scalar. So you just rescale the vector V. The direction doesn't change. So for example, if you want to find the unit vector direction of V, which is 515, so you just divide the V by the length of V. So that's 515 over square root of 5 squared plus 15 squared, That's how you find the length of V. So you get 25 plus 225, which is 250. So square root of 250, you can factor it as 5 times 10. And then, 25 times 10. Then take a square root of 5, you get 5. So you get the 5 square root of 10 at the bottom. And then just divide 5 on 15 by that. And then that gives the components of the vector. Oh, that's another typo in here. So it should not be V equal to V over length V. It should be the unit vector V equals V over length V. So I will correct that also. So 5 over 5 square root 10, 15 over 5 square root 10, you can obviously cancel 5. You get 1 over square root 10 and a 3 over square root 10. And that's the unit vector in the direction of V. And it is okay to write in that form. You don't have to rationalize those numbers. You can keep the radicals in the denominator, in other words. Okay, there are some vectors. It's called the standard unit vector. You can draw unit vector in x and y directions, and they're called standard unit vectors. And we use I and j to denote them. So obviously the vector I has component 1 in the x, and the 0 component for y, and j has 0 component in x, and the 1 in component of y. All right. Okay. So then using the standard unit vectors, you can rewrite a vector in the notation of I and j. So suppose the vector v has come to v1 and v2, and then you can split it in it as v1 0 plus 0 v2, right? If you add them, you're going to get v1 v2. Add the components separately. Okay, now you can factor v1 from the first vector and the v2 from the second vector. So you get v1 1 0, right? And plus v2 0 1. If you Well, the 1 0 is just I, and the 0 1 is j. So it could be 1 I plus v2 j. So for example, you can write the vector 3 negative 4 as 3i minus 4j. I guess you know that. Probably learned a little bit before. Okay. So So the next topic is how to decompose a vector. All right. So given a vector, how do you decompose? How do you find the x and y components? For example, if you are given the length of vector and the angle, how do you find the components? It's just like the conversion between polar coordinates and direct angle coordinates. We are using the same kind of formulas in here. So, for example, we can write V as components V1, V2, but V1 is just length V times cosine theta, and then length V times sine theta. If you look at the graph, you decompose the vector, vector V into x and then the y-axis. All right. So I wrote the length of each part. Okay. So then you can rewrite in standard unit vectors y, I and j. So that's length v times cosine theta plus length v times sine theta. But length v is just v1 squared plus v1 squared square root of that, because v1 and v2 are the components of. So we get a square root of v1 squared plus v2 squared cosine theta I plus square root of v1 squared plus v2 squared sine j. So, for example, given the length of v equal to 5 and the theta equal to 120 degrees, okay, the angle of the vector measured from the positive x direction is 120 degrees. So, how do we decompose vector v? I just use the formula in here. So, vector v is just the length v cosine theta I plus length v sine theta j. Using the formula on the top. So the length v is 5, so that's 5 cosine 120 degrees, theta is 120 degrees, plus 5 sine 120 degrees j. Cosine 120 degrees is negative 1/2, and the sine 120 degrees is square root 3 over 2. So we get the negative 5 over 2 I plus 5 square root 3 over 2 j. So that's how you use the length of the angle of a vector to decompose into x and y components. All right. So I think this section is relatively easy. So, so I don't want to discuss more problems or examples. So that's the end of this section. We're going to do section 2 next Tuesday. And any questions before we dismiss today? If no question, then I'm going to stop the recording.